So yeah, let's just get started. Thanks for everyone to come to this tutorial. So I'm Jason Dai from Intel. So this tutorial is about our work. We actually have been working with many of our users and customers to build very large-scale deep learning applications on top of big data platforms. So we'll talk about the state of art in this field, some of the example applications, as well as some real-world applications we have. So this is the agenda for today. So we'll first talk about the motivation. As I mentioned before, we have been working with a lot of users and customers to build deep learning applications on big data platforms. But why is this important? And show some real-world examples of people doing that. And then we give an overview of different deep learning frameworks, especially in the recent years, people are working to bring those deep learning frameworks to Apache Spark, one of the most widely used big data framework. So we'll talk about BigDL, TensoflowOn-Spark, DL pipelines, SparkNet, and so on. And after that, we'll give an overview of a new project. We actually just open source delivered the first open source release last week. Analytics room for Spark and BigDL. It's essentially built on top of those deep learning frameworks to build a high-level analytics and the pipeline to help people to build and productionize their deep learning applications for big data. And finally, we'll give various examples of how people build those analytics applications before the break. After the break, then we're looking into how actually people are, how those distributed training, the large-scale distributed training is implemented inside the BigDL as an example of how you can actually perform very large-scale distributed training directly on top of big data platforms. And then we are looking at more applications, including some advanced applications, as well as actually some real-world applications that we have been working with our customers. For instance, JD.com, which is a very large e-commerce website in China. I mean, just this week, Google announced they invest I think $500 million in JD.com. It's a really huge website in China. And then there is also a lot of enterprise companies have been working with AMS listings, World Bank, UnionPay, which is another very large payment company in China. We have been working with them to build a different type of real-world applications, big data applications using those deep learning technologies. And then finally, it's conclusion and Q&A. Yeah, I will upload my slide after the tutorial in the website. There is a link to the tutorial website in CVPR. Yeah. So, yeah, as I mentioned before, we have actually seen a lot of efforts, a lot of applications in the industry which actually try to bring those deep learning capabilities to their big data platform or big data solutions. But why do we want to do that? So we'll first talk about the motivations. We see that it's actually a result of several important industry and technology trend, which drives these efforts of running deep learning applications for big data. And we will show one real-world example of how this actually looks like in the real world. So first of all, we see some of the important motivations. Well, you have probably already seen this chart from Andrew's book. Basically, this actually shows one of the key reasons why deep learning is so successful, so effective today is because of a large amount of data we have access to today. I mean, the y-axis is essentially the performance or the effectiveness of the model. The x-axis is essentially the amount of the data. So it's not entirely accurate, but essentially it gives the idea that today people are building even more complex, even deep neural network models, which can take advantage of the massive amount of data we have. So essentially, it is critical that those deep learning applications, deep learning systems, they need to be able to take advantage of the massive amount of data we have. And then secondary, if you look at the industry, I mean, if you go to all of the big organizations, whether it's a large internet company like Facebook, like Google, like Alibaba, or even some more traditional enterprise type of company. In this case, we're showing two examples from British Telecom and Goldman Sachs. Basically, today, in the industry, Hadoop, Apache Hadoop, you probably have heard about Hadoop, but in this sense, it's not only about the Hadoop project, it's more of the vast Hadoop ecosystem. It includes many different open source projects like Hadoop, Hive, HBase, Spark, and so on. The Hadoop ecosystem is becoming the standard of how people store, process, and analyze their data in production. I mean, here it gives the word that Hadoop becomes the center of data gravity. I mean, if you think about the data as a ball, you put it on the surface, it will just roll down to the lowest point in the surface. It's kind of like that. People, especially in the industry, in the internet company, in those large enterprise companies, they are building their data center, data hub, data platform using the Hadoop big data platform, and it becomes the one place where all the data, all of your history data, all of your unedited history data are located. So any data analysis tools, any data analysis systems need to be able to interact with the Hadoop ecosystem and process the data, and including those big data frameworks. If you need to access a huge amount of data, especially the production data, you need to be able to seamlessly integrate and interact with your big data system, which is basically based on Apache Hadoop and Apache Hadoop ecosystem. Well, the trend number 3, this is actually from a Google NIPS paper from Google. Essentially, it talks about, well, we are, I'm not sure if you can see it very clearly here from there, but essentially, the black box here, which essentially is your machine learning code or your deep learning code, essentially it is the model we are all excited about. It's critical in that it gives you unique capabilities to perform various interesting algorithms on top of your data. But to build and deploy a real-world machine learning or deep learning system is actually far more than a piece of machine learning or deep learning model. You need to actually have the entire data analytics pipeline from data ingestion stream, data cleaning, and also the feature transformations, and then resource allocation, monitoring, and so on and so forth. The surrounding infrastructure is huge. I mean, it's a huge challenge. I will actually talk some examples of how challenging it is actually to deploy and productionize a deep learning models for your big data in production. I mean, the model is critical, but in terms of the efforts, engineering effort you spend to actually production and deploy the end-to-end pipeline, a lot of efforts need to go into those components, and this is where the big data processing pipeline, big data analytics pipeline come into picture, because a lot of those problems has actually been solved by those big data systems, and we really need to have those deep learning algorithm models well integrated into this big data pipeline, big data workflow. Well, trend number 4. I mean, this, about probably 5 years ago, when you look at the big data systems, there are actually many independent, specialized big data systems. Some are good at batch processing, some are good at streaming processing, some are good at SQL queries, and so on and so forth. So this is an analogy by Ian at UC Berkeley. Basically, think about that. I mean, we used to have a lot of those special devices, right? Your smartphone, the phones, the cameras, the GPS, the MP3, and so on and so forth. And now we have the smartphone, which kind of become the unified device. It's not only easy, right? You instead of bringing many devices, you just have one device. It's actually make it possible for you to build new applications. For instance, today you can build applications that combine the GPS, camera, music, all those capabilities in your one application, which is not possible if you have many specialized independent devices. So it's kind of the same for the big data system. I mean, we used to have, as I mentioned before, we used to have many specialized independent big data systems doing graph analytics, doing SQL query, and so on. Today, as I mentioned before, the Apache Spark, Apache Hadoop, it's not only the Hadoop Spark project, but it's the whole ecosystem, including for instance, the storage distributed file system, the storage table system, also the data input, input and the resource management, also the stream processing and so on. The Apache Hadoop and the Spark ecosystem kind of become the unified big data platform for people to perform different type of analytics tasks on top of one unified platform. So you have other data stored and managed in this one platform, and then you can perform different type of analysis on top of this unified platform, whether it's batch processing, it's streaming processing, it's graph analytics, it's machine learning. You can use different type of languages, whether it's Java or Python or R, SQL, or even some spreadsheet type of interfaces, which is made possible by building this type of this unified data platform with many different capabilities integrated into this ecosystem platform. So what's missing here? It's pretty clear that today it's not easy actually to bring those new deep learning capabilities or deep learning models into the big data platform. So we do see a big gap between the deep learning community versus the big data and data science community. I mean, we all see a lot of breakthroughs, and we actually kind of see breakthrough almost every week, if not every day, from the deep learning community, where you see new models, new algorithms, new use cases, which is very exciting. It's very exciting. So at the same time, so the average users who are the big data users, data engineers, data scientists, analysts, who actually want to leverage those new deep learning capabilities and deep learning algorithms. However, it's very difficult for them to apply those new technologies to their big data systems. I mean, as I mentioned before, in production, all your data is actually stored and managed in a very large distributed file system, for instance, in HDFS, which consists of thousands, if not tens of thousands of servers. So we actually have been talking to a lot of the very large users who have, on one hand, they have very large tens of thousands of servers which runs their big data systems, store their data there. And then to run those new deep learning algorithms, they have to stand up a separate independent system, maybe tens or maybe hundreds of servers. Now a big challenge for them is how they actually move data from servers running distributed file system to their probably 100 server which is dedicated to deep learning. So it's become a big challenge, a big, huge bottleneck for those users. In some cases, they have researchers doing research on their big data cluster, and they have a dedicated engineering team doing data cleaning and data transformation to bring the data from their production big data systems and copy that onto their research cluster, which is a huge overhead for them. So let's look at one example. As I mentioned before, this is one of the customers we have been working with, JD.com. As I mentioned before, it's one of the largest, actually one of the largest online shopping website in China. This is one particular example. Applications, what they try to do is basically doing very large scale image recognition, feature extraction in production. I will talk in more detail about this application later. But to look at this problem, they have hundreds of millions of images which are stored in HBase, which essentially is a distributed table storage built on top of Hadoop on top of HDFS. So they have hundreds of millions of images stored in HDFS. And then they need to get the image out of the HBase and perform various pre-processing on those images in a distributed fashion. And then they need to run some model. In this particular case, they are running some SSD models to get some result. After that, they will perform another large-scale picture pre-processing and transformation to crop the image and doing a bunch of other pre-processing and run another, in this case, deep bit model. And finally, they need to store the result back to their HDFS, their distributed file system. So if you look at this end-to-end pipelines, you have all those data managed by your distributed storage, distributed the table, and you need to store your data onto the HDFS, store your result back to your distributed file system. And you need to, once you get those hundreds of millions of images, you need to do a lot of distributed image pre-processing, in parallel across a very large cluster before you actually run those models. So as you can see, this actually clearly shows that it's critical that you need to integrate your deep learning model, deep learning algorithm into your end-to-end big data processing pipeline or workflow. And then secondly, you need to be able to run those algorithms directly on top of the big data systems instead of copying the data out, because copying hundreds of millions of images is no fun. And this clearly shows that there is a lot of requirement, a lot of need for people actually to bring those deep learning capabilities to their big data systems. And we'll talk about how in the next sections. So to summarize, the goal here is we really want to bridging the gap to make deep learning more accessible to the big data and the data science communities. So first of all, a lot of them can continue to use their existing tools, the existing big data tools and the infrastructures to build those new deep learning applications. Secondly, you can directly analyze your data, run those deep learning models, algorithms on the same class, on the same Hadoop cluster where the data are stored, instead of transferring data between different clusters. And you really want to add those new deep learning capabilities, deep learning models into your existing big data program of workflow. And the other part is probably less obvious, but if you go to a lot of the organizations, they already stand up, as I mentioned, thousands or tens of thousands servers to store the data and process the data in their big data systems. And it's critical for them to actually, they can reuse their existing Hadoop cluster to run those deep learning applications, new deep learning applications. And those deep learning applications can actually share the results with other workloads. For instance, you may be doing a lot of SQL queries in the daytime, and at nighttime, your cluster kind of less busy, and you can run those machine learning, ETL, and including deep learning applications. So different type of workload can actually share the cluster in a dynamic and elastic fashion, and all those workloads can be monitored and managed by a one resource management systems. For instance, in a lot of cases, when you have high priority workload, this resource management system may go on and kill or preempt those low priority workflows. A lot of cases, those offline ETL, maybe your deep learning training tasks can be killed and to make room for the high priority tasks. So all those resource management monitoring are critical for people to actually productionize their deep learning applications. So, given that, actually there have been quite some efforts in the industry today to bring those deep learning frameworks to the big data system, especially on top of Apache Spark. I will give some overviews of those different frameworks. So first of all, Apache Spark. I'm not sure if everyone is familiar with that. I mean, Apache Spark essentially is today the most widely used cluster computing framework for low latency distributed data processing. So it's an Apache project, so you can go to the Apache website to look into details. But in essence, Apache cluster has it basically is a master-slave architecture. It has one single driver and many workers in a Spark cluster. Then you write a Spark job, which processes a huge amount of data across a cluster. So a Spark job consists of many Spark tasks. Each task is working on a data partition. So it's a data paradigm, and you have a Spark job, which consists of many different Spark tasks. Each task working on a separate data partition. The driver node is responsible for scheduling and dispatching the tasks to the workers. And the workers runs the actual Spark tasks. So as you can see here, on the driver node, you write a program which launches the Spark job. And the Spark job consists of many different tasks. And the driver node is responsible for scheduling and dispatching tasks to the workers, which actually run the actual compute. Yeah. So this is how what a Spark program or a Spark application actually looks like. So you have, as I mentioned before, you write application. Your application actually runs on the driver node, and inside your application you will include the Spark as a library. In this case, it's Spark context, which manages all those Spark resources in the Spark and tasks. And since the Spark context will actually interact with the cluster management tool, you can run it actually on your laptop, on a local node. I mean, it's just run on multiple threads. But usually you actually run it across a cluster, so it can run on a Kubernetes cluster, on a Yarn cluster, on a Mesos cluster, or it's on its own standalone mode. So the Spark context interacts with the cluster manager, which interact with all those workers. So those workers can be managed by whatever cluster resource management tool you have. And it can access the distributed file system through the Hadoop API. It can use HBase, HDFS, S3, Azure, and so on. So this is this is conceptually how a Spark job looks like. It's basically as I mentioned before, in Spark has a data parallel execution model. So all the data set is represented as RDD, so-called the resilient distributed data set. You can think of RDD as a distributed set of Java objects or Python objects. So it's have a collection of Java objects or Python objects, but it's a distributed across partition and distributed across the cluster. So in this case, say there is A, B, C, D, E, F, G. It's actually seven RDDs in this picture, and in each RDD, the data is actually partitioned into disjoint set. And then a Spark job essentially is represented as a general computed graph, a DAG, where each node is an RDD, and between those RDDs, the edges actually are transformations, whether it's a group by operation or map operation and so on. So in this in the Spark computing model, all the RDDs are immutable. You cannot make changes to the RDD. You can only transform one RDD into a new RDD, and then you perform the transformation to compute your result. So in this case, as you can see here, in this case, you have 7 RDDs, and for instance, RDD-B is computed by performing a group by on RDD-A, and so on. And then some of the transformation is pretty straightforward. For instance, you can perform a functional map operation, just like the map operation in MapReduce. You perform a map operation which you direct. It's essentially completed data parallel, right? You can directly perform the compute on the local partition. But for some of the operations, for instance, group by or join, it's more expensive because you need to repartition or shuffle your data across the network to perform a group by or join operations. So depending on what operation you have, essentially the computing graph can be divided into different stages. So in this case, you have 3 stages. Stage 1, stage 2 is doing the oops, cannot see that. Stage 1. Stage 1 is working on this RDD. Stage 2 is computed so different RDDs, and stage 3 compute the final result. So you basically each stage has is a new task. So you can only compute stage 1 and stage 2 before you can compute stage 3. And inside each stage, it's the computer is performed in a data parallel fashion. So, for instance, in stage 2, it actually launches 4 tasks. Each task will work on a partition of the data. So you can have 4 tasks run in parallel to compute stage 2. And another key characteristics of Spark is essentially it's used in memory caching extensively. So in this graph, the green block shows a partition which is cached in memory, for instance. So Spark will manage your data and take your hint and cache some of the data in memory. So if the data is cached in memory, it does not need to be computed again. So in this case, actually stage 1 is not needed because the result of stage 1 is already cached in memory. So you can directly read the data from the memory and skip the computer of stage 1. So hopefully this gives you a high-level overview of the Spark computer engine. So as I mentioned before, Spark is actually one of the most widely used data analytics big data processing framework in the industry. And this is a project open sourced by Intel, BigDL, which essentially build a deep learning library directly inside the Spark. So if you're familiar with Spark, actually Spark, I mean, we talked about the core computer engine of Spark in the last couple of slides. And on top of that, it has many different libraries for different type of data analysis. For instance, SQL query, R support, streaming support, machine learning, ML lab, GraphX, which performs the graph index. And on top of that, you have machine learning pipelines and the DataFrames. And BigDL is implemented as a standard library, just like MLlib or Spark SQL, which runs directly on top of Spark. So basically, you can write with BigDL, you write your deep learning applications as a standard Spark program, which just directly run on top of existing Spark or Hadoop clusters without any changes. Well, it has all those deep learning functionalities similar to other frameworks, and it's specially optimized for Spark or big data cluster, which essentially, on one hand, it's runs on very large servers. So it's use Intel MKL and a lot of multi-thread programming to actually to achieve high performance on a single node on CPU, and it also leverages Spark for very efficient scale out, so it can scale out a larger number of servers for training and inference. So Yeah, I mentioned before, BigDL runs as the standard Spark program, so no changes to the Spark Hadoop class needed. So it's a iterative process. Let's look at this picture first. So you write a BigDL program, which is essentially a Spark program, but with the BigDL library. And inside the library, we have a Spark library to launch many Spark tasks. And those Spark tasks will, again, use the Spark BigDL library to perform those neural network computations, which under the hook use Intel MKL to do all the mass computation. I mean, MKL is basically the mass kernel library from Intel, which is probably the fastest mass library on Intel platforms. So it's an iterative process in that each iteration of the training, basically the training is an iterative process. So each iteration of the deep learning training is run as actually multiple Spark jobs. And it's also data parallel. It's essentially using a data parallel model. So each Spark task will have the same model, but it works on a subset of the data. And it supports both inference and the distributed training. The distributed training is actually implemented using a parameter server type of architecture, but it's not theoretically it's not a parameter server per se. It's actually uses the block manager and other primitive inside the Spark to implement AR reduced synchronization mechanisms. So it kind of provide a parameter server type of architecture for synchronous minimatch SGD. I will talk about the details later, but this is essentially it supports distributed training by providing a R-reduced synchronization for a synchronous minimatch SGD. Well, next there is from Yahoo. I mean, besides BigDL, Yahoo actually has an open source project called the TensorFlow-on-Spark. It essentially use a Spark cluster or Hadoop cluster and then run those standalone TensorFlow jobs on that cluster. So it uses Spark as the orchestration layer to allocate many different resources. Essentially, those server nodes or worker nodes. And then once the resource allocated to the Spark job will actually launch a independent standalone TensorFlow job, which runs on top of the allocated resources and in a distributed fashion. So as the figure here shows, I mean, there are two modes. One it actually uses feed deck to feed the data into the TensorFlow job. The other one is actually use queue runner, which allows the TensorFlow work to directly read data from HDFS. So let's look at this one, the feed deck. So basically, as I mentioned, you have many different workers in a Spark cluster. So each worker runs a Spark task. The Spark task will first launch the TensorFlow processes. Some are worker in TensorFlow, some are the PS task, some are PS task in TensorFlow. And then the Spark task will actually get the data from, for instance, from HDFS or from other data source, and transfer the data through a Python multiprocessing queue. So essentially, those Spark tasks and those TensorFlow tasks are running as independent Python processes. So they are communicated through some inter-process communication mechanism. In this case, is Python multiprocessing queue. So it will put the data into the Python queue, and the TensorFlow worker will get the data from the queue, and then the TensorFlow workers and those PS tasks will communicate basically by themselves to run the TensorFlow task jobs in a distributed fashion. And then another mode, essentially, instead of having the Spark task feeding data through the queue, it will in the queue runner mode, it essentially runs those TensorFlow worker and the PS functions, the PS tasks inside the task, but they will communicate through each other and they will read the data directly from HDFS. So this is how this the TensoflowOn-Spark at a high level is implemented. It essentially uses the Spark as the orchestration layer to launch the TensorFlow jobs, and the TensorFlow jobs will get the data either from HDFS or from those Python queues. So it's a kind of a cross integration of two independent frameworks, right? You use the Spark to do the resource allocation, and then you have the TensorFlow jobs to run on their own. So there's some so it's a nice way to run distributed TensorFlow jobs on your Spark or Hadoop cluster. It has some problems. In this case, it has some memory overheads. It's kind of not very efficient to transfer data between two independent processes. And another limiting factor is that you really need to launch all those TensorFlow tasks all at once. It's kind of the Gantt scheduling is required. You need to schedule all those TensorFlow tasks. Otherwise, you won't be able to run your job, which is different from a typical big data job where the tasks are scheduled incrementally. So you do not really need to launch all your big data tasks all at once. And it has some limited interaction between the data processing pipeline and the training pipeline, for instance. You need to communicate through some constrained interfaces. So it's an open source project available on GitHub, so you can take a look at it. This is a project open source by Databricks called Deep Learning Pipeline for Spark. Basically, it takes advantage of the Spark and machine ML pipeline. So if you are familiar with the Spark ML pipeline, it's kind of like the pipeline constructor inside scikit-learn, for instance, but it's just implemented on Spark and run in a distributed fashion. So inside, so as I mentioned before, it's like a scikit-learn pipeline. You have a pipeline consisting many component node in the pipeline, which performs the machine learning tasks. So you have other transformers which essentially transform their data. So whether it's load data, it's some pre-processing of data, or using the model to do some inference. Essentially, it takes the input and transform it, generate the output. And then there is another type of component called the estimate, which essentially is a model. You can fit the model on the data, and it use the data frames, the Spark data frames, as the input output of each component, and then you can essentially construct a pipeline which allows you to perform end-to-end machine learning processing, whether it's inference or training. And the deep learning pipeline for Spark essentially provides support to load existing TensorFlow or Keras models into your Spark ML pipeline. So you can load a model, TensorFlow model into a transformer. In this case, it's a transformer. So, which means you can use the TensorFlow Keras model to perform inference. It also can load those models into estimate. However, it does not support distributed training. You can, once the model is loaded into an estimate, you can perform some single node training or fine tuning. You can run many instances in parallel, but there is each of them is running on a single node mode only. So it's kind of single node training and tuning only. So there is no distributed training. The other example is a kind of a research project, SparkNet, which is probably one of the first to do the distributed deep learning training. It basically has many, well, as I mentioned before, there are many workers, and inside each worker it actually runs a cafe instance doing the training, and it's asynchronous. It's an asynchronous parameter synchronization in that on each node the cafe instance will run many iterations to update its weight, and after several iterations they will send the weight to the master to do average, and then the master will distribute the new weight to each node. So it's an asynchronous parameter synchronization, which and the weight averaging at the master side is kind of inefficient, very inefficient. So it's a interesting research project, but really not that useful for large scale processing. So we talk about all those different deep learning frameworks which people bring to the Apache Spark. So basically, the goal is really to make those deep learning frameworks running on top of the Spark cluster so that it can directly access the data on the cluster. But to build the end-to-end deep learning applications for big data, you really need to build out the entire pipelines, end-to-end pipelines for your applications. This is what we have been working on. We just released this new open source project called NX, which is supposed to be a high-level analytics and AI platform for Spark and BigDL. It makes it try to make it easier for users to build and productionize those deep learning applications for big data. So it uses different frameworks at the backend, Spark, BigDL, TensorFlow essentially. And on top of that, it provides those high-level pipeline APIs for people to build out their end-to-end pipelines and productionize their model. And then it provides various built-in feature engineering operations as well as deep learning models. So you can directly use inside your application. And it also provides several different reference use cases for instance, for anomaly detection, for fraud detection, and so on. So it's an open source project on GitHub, and you can take a look for the detail. So here's how it works. First of all, as I mentioned, it makes it easier for people to build those end-to-end deep learning applications for big data. So you can build your end-to-end data analytics plus deep learning AI pipelines using Spark natively in Spark DataFrame and ML pipelines through the nnframe package inside the NNSU. And it provides flexible model definitions. You can use autograd, Keras style. More importantly, to transfer learning APIs to build your models. And you can process your data using all those built-in feature engineering operations. And you can directly reuse some of those built-in models and reference use cases for your as an out-of-box solution for different problem types. And to make it easier to productionize your deep learning models and deep learning applications, it provides a pre-ordered Java object type of model serving API so that you can directly serve in a model from the web service or even from some other big data frameworks. For instance, you can directly use it in Storm or Kafka as a streaming processing. And it can directly, it essentially runs those distributed TensorFlow models on Spark inference, as well as actually fine-tuning so that you can directly integrate your TensorFlow models inside your Spark programs, which runs those basically productionize your TensorFlow models across many different nodes and servers in your cluster. So let's look into some of the details. nnframe is a package which in analytics which provides a native deep learning support in Spark DataFrame and the ML pipeline. So this shows some examples. First of all, you can initialize your own context, which is a wrap of the Spark context we just saw. It essentially wraps the Spark context and to provide various configurations and tuning points for running deep learning algorithms. And in this case, you can load images directly into a data frame. So in this case, you can basically have a large image set whether it's on HDFS, for instance, HBase, and you can directly load that into a data frame. And once you have the data in a data frame, you can actually use the data frame operations to process the data. In this case, for instance, you can. So data frame is kind of like a SQL, a relational table with many different columns. So it's actually very easy for you to process your data. For instance, you can get the name of the image and you use the name to generate a new column. So you load a image, you can add a column for the names of the image, and then you can add another column to generate a label of the image and so on and so forth. And then you can process the image using the built-in feature engineering operations. In this case, you can basically transform the normalize the image and so on and so forth. Then you can define the model. It provides a Keras style API. Basically, you can define a very simple, say, convolution neural network model, and then use a estimate. Basically, using the Spark ML pipeline, you can build an estimate and the fit on your input data. So this essentially provides leverages the Spark DataFrames and the Spark ML pipelines to build out the end-to-end data processing process, but to provide native support for deep learning. Well, and then to build out the pipeline, of course, you now you have the construct, the nnframes to Spark DataFrames, the ML pipeline to build out the end-to-end pipeline. So you have the construct to build out the pipeline, but you need to have a model to define model for the pipeline. So it provides a AutoGrad, Keras, and the TensorFlow API for you to do that. This shows an example of how you can build a simultaneous network using the transfer learning, using those APIs. First of all, you can use the API to load the existing model. It actually provides support to load a BigDL model, Cafe model, TensorFlow, Keras, or Touch models directly into Spark. So you can in this case, you directly load the existing Cafe model. And then you can remove several layers. This is supposed to be an inception V1 model, for instance. You can remove some of the models after the pool 5, the layer of pool 5. So you can generate. So once you load the model, you can generate a new model, which in this case the output is pool 5. And then you freeze all those layers up to say this one. So you can freeze the layers in this new model up to this layer, and then you can append a few new layers. In this case, you basically okay, we're showing it the resonance model. Anyway, you have a model. You basically have an input, and then you add several new layers, flatten and so on. And then now you can use the AutoGrad and the Keras style API to build out the semantic network. Just remember, we just basically we load a pre-trained resonance model, and we remove several last few layers, freeze the first few layers, and we transform it a little bit. We get a resonance model, and then now in this case we actually. In a semantic network, you basically have each input is 2 images, right? The image is similar, so those 2 images are either similar or not similar. So basically, the input has 2 images. So it has it's a 4D tensor. The first dimension is actually have 2 elements. First one is one image, and the second one is another image. So you get 2 images as the input. In this case, we actually use a time distributed layer, which is similar to it's actually the same as the time distributed layer in Keras. You can build the features. So the features is essentially, again, you can select the first. You can do an index select from the feature, which is the feature for the first image, and this is the feature for the second image, and then you can compute the the absolute of the difference of those two features. So basically using a autograd operation to do that, and then finally you can build a model. In this case, you basically push the input is 2 images. You have this model. You just load a pre-trained resonant model and use that to compute the features for those 2 images, and you compute the difference of those 2 images, of the features, the absolute of the difference of the images, and then you generate a sigmoid, and then you build the model, and then you can train the model to basically to have the network to learn how similar those 2 images are. Well, so in addition to the model, to building a model, you also, the end-to-end pipeline also involved a lot of building in feature engineering operations, and you can do that actually. We basically in NNFrames provide a lot of built-in image transformation operations, which essentially run OpenCV in parallel on Spark. So all those operations, for instance, all those operations that essentially under the hook utilize the OpenCV libraries and run in parallel across a large cluster. So you can essentially use the OpenCV operations to actually build out your image augmentation and feature engineering processing. It also provides a lot of built-in deep learning models, including object detection. For instance, it provides the pre-trained models and a high-level API for use to build out your object detection applications, and also image classification models, test classification model, and recommendation model. There are actually a lot of use cases on Spark, which is actually process the structured data, your transaction log, your history log, and the recommendation actually turn out to be a very popular use cases. And we provide 2 models. One is the neural caliper filters. The other one is wide and deep learning for people to use for recommendation. So this is a very simple example of how you can use the object detection API in NNFrames to perform off-the-shelf inference. So basically, you first load the pre-trained model into the in the detection model zoo. So you load the model, and then you can off-the-shelf inference use the load model. You basically, for instance, you read the data into image set, and then you just predict to generate an output, and it provides a visualization utilities from the model, get all the configurations which provides all the label maps. So some of the models are pre-trained on the MS COCO data, some are pre-trained, for instance, on the Pascal VOC data. So you have different labels. You can get a label from the model, and you visualize it on your image. It's essentially draws all those bounding box on the images, and you can show that. There are some examples and notebooks that we will look at that later. There are also a collection of reference use cases for anomaly detection, for fraud detection, for recommendations, sentiment analysis, and VA type of work. So for many of them are actually based on, for instance, those anomaly detection, fraud detection are based on the solutions we have been working with our customers in real world, and we abstract their models and processing pipelines and port that over to some public data set, so that you can take those reference use cases as end-to-end applications and adapt that to your application. As I mentioned before, in addition to building those end-to-end pipelines, Analytics also provides a lot of support for you to productionize your deep learning applications. For instance, serving the models. It provides a pure Java, a pre-old Java style model serving API, so that it can be directly utilized in your, for instance, web service. So this is a pure Java. You basically extend this interface And then you can load the model using that in this abstract inference model, and you use the JTensor to do the prediction. Everything is done in Java, so that it's very easy for you to integrate with those web services, as well as other big data frameworks. For instance, in this case, Storm. You can basically integrate the analytics models in your Storm operators, which allows you to do those real-time stream processing. The other, in addition to those, to that, I mean, you, as I mentioned before, BigDL, it runs on BigDL and it uses Spark inside the Spark, natively inside the Spark. So it's basically you can use the Spark DataFrames to do the model serving in a very straightforward fashion. In this case, you can define a UDF to wrap your analytics model, and then you can actually use it inside your SQL query or DataFrames. Let's say you have a database of images, and you can actually write a UDF to wrap your model, and then you can directly use your model inside your data frame operation or SQL operation. So in this case, you can actually write a SQL, use that use that UDF. This UDF will basically, let's say it's a classification model. So the UDF can directly read the pixel of your image and filter out all the pictures that are dots. However, it's actually, you can do that directly in your SQL queries. So instead of writing a program, you can actually have your analyst to write a SQL query to invoke your deep learning models. So it's much easier for the analyst to serve the model to the analysts who are writing SQL. Well, finally, as I mentioned before, there is actually a lot of use cases. People take the existing TensorFlow models and need to apply it to a very large data set across a very large cluster. And to make it easier to do that by providing a TFNet API. So first of all, you can export your TensorFlow models. In your TensorFlow program, you can directly export the TensorFlow models. You basically, this is your TensorFlow model, for instance. And I think the only gotcha here is that this example is kind of arbitrary, but it demonstrates that say if you are doing a training in a batch, you really need to, instead of hard code your batch size, you really need to do something like this so that the batch size is not hard coded in your TensorFlow model. Otherwise, it makes it difficult to do the inference. But say you have the model defined, and then you basically train the model. When you're happy with the model, you can actually directly export the TensorFlow model using this utility provided by Zoo. Basically, you import this utility, and you can export your TensorFlow model directly from your TensorFlow program. This is the input of your this is the input tensor. This is the output tensor of the output list of tensor, input list of tensor of your TensorFlow model. You can export that. So inside the Spark program, you can load the exported TensorFlow model into the Spark program. Basically, you basically import your model. Alternatively, you can directly load a frozen TensorFlow model if you know the input and output names. You can just freeze the model and input that, and then you can do then it becomes a conventional BigDL model, which can directly run on top of Spark. So you can do all the other stuff that we just talked about. You can take the model, you can, well, again, in this case, you can add a few layers and build a new model and perform the prediction, for instance, in this case. Okay, I think we are a little bit behind. Probably we can take a break, and let's continue after the break. After the break, we'll talk about some of the examples of how you can build those applications, use the APIs, and especially some of the real-world applications we have been working with our customers. So let's think we have a